Welcome back, Pre-Calc. We are finishing up the 2-1 Day 2 notes. We had done the first half in the previous video, and now we're going on to something called Sandwich Theorem. Sandwich Theorem is also called Squeeze Theorem. I think you're usually going to see Sandwich Theorem, but in case you see Squeeze somewhere, it's the same thing. Here's essentially what the Squeeze Theorem is. It's an indirect method of finding the limit of more complex equations. Typically, we're going to end up using the Squeeze Theorem a lot of times with trigonometric functions, something with like sine or cosine, stuff like that. So here's what it says, and then I'll draw a picture so you kind of get a visual of what's going on. So if g of x is less than or equal to f of x, which is also less than or equal to h of x, for all x not equal to some value c, okay? So in other words, if you look at this, f of x is sandwiched in between, b slash w is between g of x and h of x. Between g of x and h of x. Okay, so if you have this function that's kind of sandwiched in between these other two functions, and the other thing that has to be true is the limit as x approaches c of h of x is equal to the same thing as the limit as x approaches c of g of x. If both of those limits as x approaches c equals L some limit, therefore the limit as x approaches c of the sandwiched function f of x is also going to equal L. That probably doesn't make a whole lot of sense at the moment, so let me draw a picture so you can kind of see what's going on. So let's say that we have some function. I'm just going to draw it in red. Let's say that this is h of x. All right. And then let's say that we have this function g of x. And then we have this function f of x that's going to be kind of sandwiched in between them. So something like this. All right, so those are our three functions. And let's say that this point kind of where they all kind of congregate here is at c. All right, so here's what happens. You can see that f of x is in between h of x and g of x, everywhere except for at c. All right, so this green line is between the red and the blue line. So that's this first part. It's sandwiched. And if the limit as x approaches c of h of x, all right, so the limit as h of x, the limit as x approaches c of h of x, you'll see it's approaching this, as it approaches c, it's approaching whatever this y value is over here. I don't know what it is. The limit of g of x as x approaches c is also approaching that same y value. All right, and so if the red function and the blue function's limits are equal to the same L value, whatever that happens to be, then the sandwich function also has to have the same limit. And hopefully you can kind of see that. If you take the limit of this green line as x approaches c, it's also approaching the exact same y value. So if the f of x is sandwiched in between them and the limits of the g of x and h of x are the same, then the limit of f of x has to also be that exact same value. And I will show you that with this guy. Okay, so the problems are usually going to say show, it's kind of like a proof. We're going to show that the limit as x approaches 0 of x squared times sine of x is equal to 0 using the sandwich theorem. Okay, so what we're going to do is we know that the sine of anything, so the sine of whatever you want to say, sine of anything, is always going to be between 1 and -1. If you remember our unit circle, the biggest it could ever be is 1, and the smallest it would ever be is -1. All right, so what we can do is there is an x squared out in front. We'll deal with that in a second. But the sine of anything, so in this case, the sine of 1 all over x has to be greater than or equal to -1, less than or equal to +1. However, we're not just doing the limit of sine of 1 over x, we're doing the limit of x squared times that. So what I'm going to do is I'm going to take this inequality and I'm going to multiply it by x squared, because that's what's going on here, is the sine of 1 over x is being multiplied by x squared. When I do that, I'm going to multiply all three sides. You get -x squared less than or equal to, we get x squared sine of 1 over x less than or equal to x squared. All right, and so now we've kind of created an inequality, which is kind of following our sandwich theorem. So this middle function is sandwiched in between the -x squared and the x squared. What we're going to do is find the limit of each of these pieces on the outside, and as long as those limits are the same, then we know that this middle function's limit will also have the exact same value. So let's look at this. If we do the limit as x approaches 0 of -x squared, all right, this one you can just plug the value in, you're going to get 0. So we know the limit as x approaches 0 of -x squared is 0. If we do this guy, the limit as x approaches 0 of just x squared, plug the value in, you're going to get 0. So then by the sandwich theorem, because this guy is sandwiched in between these two functions, and these two outer functions both have the same limit as x approaches 0, therefore this one has to have the same limit. So therefore, these three little dots means therefore, the limit as x approaches 0 of x squared times the sine of 1 over x has to equal 0. It has to equal what the other ones on either side of it are. All right? And that's how you show it. All right, we'll do another example with number 4. So with number 4, we're going to find the limit as x approaches 0 of x times sine of x using sandwich theorem. So once again, what we're going to do is we know that the sine of anything is between -1 and 1. We have currently a sine of x. So sine of x has to be between -1 and 1. And with this problem, we don't have just sine of x, we have x times. So what I'm going to do is I'm going to multiply this by x. We end up with -x less than or equal to sine of x less than or equal to x. All right, so we currently have this function, forgot the x. We currently have this function that is sandwiched in between -x and x. We're going to take the limit of both sides, and they should equal the same value, and then therefore we can conclude that the middle function here also has the same limit. So the limit as x approaches 0 of -x, if you plug it in, you're going to get 0. This guy, the limit as x approaches 0 of +x, if you plug in 0, you're going to get 0. Since these two functions both have the same limit, the sandwiched function must also have the same limit. So therefore the limit as x approaches 0 of x sine of x has to equal 0. Right. So hopefully that kind of makes sense. Last couple problems here do not deal with sandwich theorem. We've got draw the graph, find the left-handed and right-handed limit, and then does the limit exist? Okay, so drawing the graph, you got to remember how to draw your little piecewise functions. X is less than 2, so we're going to plug in 2 and other numbers less than that. So if you plug in 2, you're going to get 1, so 2, 1. Something smaller than 2 would be like 1. 3 minus 1 is 2, so 1, 2. We know it's linear, so I'm just going to go from there. At 2, when we plug in 2, 1, we're going to get a whole. So let me make that a whole. All right, because it's not equal to 2. So 2, 1. When you plug in 1, you get 2. If you want to plug in 0, you can. You get 0, 3. All right, so the graph's going to look something like that. At the next value, you have x equals 2, and you have 2. So that means when x is 2, you have a y value at 2. So at 2, you're going to go up here and put a value here at 2. All right. And then we have our last function. Our last function is x is greater than 2, and it's x over 2. So you're going to plug in 2. And when you plug in 2 here, you're going to get a whole because it's not equal to 2. 2 over 2 is 1. So we're going to have a whole at 2 over 1. or 2 comma 1, I mean, which is right here. And then if you plug in 3, you're going to get a decimal. I'm going to do 4. If you plug in 4, 4 over 2 is 2. So at 4, 2, you'll have a point. If you want to plug in 6, you could. So at 6, 3, you'd have a point, and so on and so forth. So it's going to look like that. All right, so there is our graph. And we're going to find the left-handed limit and the right-handed limit. So what we're going to do is, for the left-handed limit, okay, we're going to find the limit as x approaches 2 from the left side. So that little negative means for the x side of f of x. Okay, you don't have to write the whole thing, just of f of x equals. And then for the right-handed limit, we're going to do the limit as x approaches 2 from the right side of f of x. All right, so let's look at this. The limit as x approaches 2 from the left side. So from the left side means we're going to be kind of dealing with this left piece. As we approach 2 from the left, we're getting closer and closer to this hole, which has a y value of 1. So that limit's going to equal 1. The limit as we approach 2 from the right. So as we follow the graph, right, and we go from the right, we're getting closer and closer to that hole, which has a y value of 1. All right, it doesn't matter that there is a point up here. We're just following the graph. So both sides of the graph are approaching the hole, which have a y value of 1. Does the limit exist? All right, since the left-handed limit equals the right-handed limit, we know that it will exist. All right, so yes, the limit as x approaches 2 of f of x exists. All right, and it will equal 1. All right, it's going to equal 1. All right, it's going to equal the same value that the left-hand and the right-handed limit are equal to. Okay, the last problem. Okay, this last problem is going to require you to remember your graphs of cosine and secant graphs a little bit. So you might have to go back and reference those. So first off, we got to graph this thing. The cosine of x. All right, so if you recall, cosine graphs, they kind of went between -1 and 1. All right, and if you remember just basic graphs, we had it split. We did like pi over 2, pi, 3 pi over 2, 2 pi, etc. I'm just going to go pi over 2 in each direction a little bit. And so for the cosine function, we're going between -pi and 0. Okay, -pi and 0. So at 0, if you remember, cosine has a high point. Pi over 2 would be an intercept, and -pi would be a low point. Okay, it is not equal to 0, so actually this point up here is going to have to be a hole. All right, so it's going to look like that. All right, so that's part of our cosine graph. Now secant graphs, we're going to go between 0 and pi. Secant, remember, is the reciprocal of cosine. All right, so if you need to remember, you know, your unit circle a little bit, you're going to have these values. All right, and so secant is 1 over cosine. So at 0, 1 over 1 is just going to be 1. So we end up kind of filling in this hole right here. At pi over 2, all right, 1 over 0 is undefined. So that's going to be an asymptote. All right, and then at pi, 1 over -1 is -1. If you remember, the typical secant graph kind of looked like this. You had a bunch of, kind of look like parabolas. So this is going to go like this, and this is going to go like that. All right, so I'm just drawing part of the secant curves. So now we have to figure out at what points does the limit exist. All right, so what we need to do is look at the left-hand and the right-handed limits. Okay, so any point in between -pi and 0, you'll notice that if you approach like -pi over 2, from the left side and the right side, you're going to definitely be approaching the same value, 0. The only place where you're not going to have a limit exist is along this lovely little asymptote. So go ahead and watch the next video because I have run